All right. Yes. Welcome to the next lecture, which I will be holding about the topic of scene representations using scene graphs. So in general, this lecture will be more into the context of robotics and more what like I and my colleagues do in our group. And one of the most important things is scene representations. Like how can we represent scenes for robots so they can understand them? And before we get to the graph stuff, we will talk about image-based scene representations because this is the go-to thing, right? I have some cameras, I get some images, I feed them to my robot, and he does whatever tasks he needs to. So if we have our little robot here and give him a task, for example, bring me the sliced tomato, and I now give him the image, which could look something like that or anything, whatever, which is our observation from the environment. Now the question is, what does it do with the image, right? It's just raw sensor input for the robot. It does not really know what to do with it. So to actually execute the task, he or the robot needs to understand its environment to actually complete the task. So what can we do with an image? Well, we could use, for example, the pixel values of an image as a representation and just flatten it into one vector and put this into our model. What is like a problem with this approach? Yes.
Incredibly high dimensional.
Yes, because we get the width and height and the channels as an input number. So even with a small image, let's say 40 by 40 by 3, it's still a huge vector which the robot needs to incorporate. And it does not capture any relevant features, right? It's just some random RGB values. Like if there's anything red in the image, could be the tomato, could be also a pepper, or maybe the oil, which is reddish. So the robot has no idea what to do. So the easy solution we can do is use actually a network to get a representation which is usable for our robot. In this case, for images, very simple, a CNN. Could also be a vision transformer or anything that produces like an embedding of an image. In this case, CNNs usually have some output at the end. We do not care about this output, right? I don't need to know if there's a cat in the image or not. Doesn't matter. I will use either this or this representation, which is maybe a 1000 sized vector. And this I can actually input in the image. And here I can be sure if the CNN is well trained, that there are actually features in there which are relevant, right? That maybe the model focused on, if it's the tomato related task, that it's focused actually on red shapes, which actually also look like a tomato. So now our robot is happy. He has a representation he can work with. He can actually execute the task because we have now an image embedded vector. But if we look at the interpretability, we as humans, well, it's still just numbers, right? Like an image is nice, we can look at the image, but as soon as like it's usable for the robot, it's not understandable for the human anymore. Because, well, numbers are numbers. I don't know if like these three numbers relate to the tomato or something else. No idea. So the question is, what can we do to actually improve this? And well, first off, we could use saliency maps, right, which we talked about yesterday, to see what region in the image is important when I have the embedding and then the actions. But there are some downsides to using that one, because for one, it's a blurry and imprecise localization of explainability, right? Like we see, okay, this region was maybe important, maybe this one. So if, for example, we have the tomato task and it actually focuses on the tomato, great. But if it focuses also on other objects, we're like, well, I don't know, maybe it's not ideal. Maybe there are some issues with the data. It's also a post hoc method. So we try to explain the model itself, and we don't really incorporate this explainability in the model itself. So the model learns on such explainable things. So it could be also an illusion of explainability. And the explanation is visualized on the image, but does not directly or not necessarily explain the image vector itself, right? I still don't know what values in this image vector actually refer to specific objects. I only know like what the model thinks is important in an image if I input it. So can we improve that? And the answer is, of course, yes. Otherwise, we would be finished here. We can use graphs, which is the whole lecture about. So first off, we look at a graph-based scene representation, and then later on talk about how we can use that in robotics. Do you have any questions for the introduction part yet? It's straightforward. Perfect. So graph structures you can actually observe in many different forms. For example, any social media friend network is just a very big graph, depending on how many friends you incorporate that. Or if we look at molecules, also nothing else but a graph. And even if we look at images, it's also just a very structured graph, right? Like I have my pixel upper left, and then I have connections to the lower right. We could also go on like text is a graph. Like there are some papers or some things out there that the transformer is nothing else but a graph, right? Because I make connections with attention between different words. So there are very many different applications. Like yesterday, Pascal Friedrich talked a little bit about GNNs. Who of you has heard about GNNs, like graph neural networks, before yesterday? All right. That looks good. So I will just go over quickly what a GNN is and how it works. So in general, we have two problems with graphs, which also Pascal Friedrich yesterday told you. For one, graphs not necessarily have to be the same size all the time, right? I can have a graph with 10 nodes, I can have a graph with 1 million nodes, depends on my data set. So we need some network which does not depend on a specific input. So an MLP, for example, you should always know how large your input is. With graphs, that doesn't work. We could use now CNNs where we can actually downsample it, right? But the problem with CNNs is they rely on structured input. They need to know the first pixel is upper left, second one there, and so on and so on. And for a graph, it doesn't care. Like if you think about the social media example, for example, you as a person could be the center of your graph, but also another person is its own center of their graph, right? So there is no real structure in there, no real order. So we need something or some neural network which does not care about the size of the graph and has some permutation invariant learnable function. And well, people came up with the idea of graph neural networks. So our network uses a graph and learns on the graph, but it's not actually a graph, right? Like, don't get confused with this image that like the graph neural network is actually a graph-based or a graph-like neural network. It's still that we look at the different nodes and say, okay, if I want to update the information from this node to the next layer, I look at its local neighborhoods. And then I try to aggregate information from the local neighborhood and from itself, and then put it through a learnable function. And this could look something like this, right? A very easy example. We are the node here in the middle. We want to update, of course, every node in every layer, right? But you need to start at one node. So let's say we update this node. So this node asks, hey, what are your current values? What are your current values and what are your current values? In the beginning, this could be anything, right? Like maybe the size of them, where they live, whatever. If we think about robotics, could be where's my current end effector or anything else, like any node features we have. And during the layers, well, they get projected into a higher dimension, right? And then we aggregate again and again. And the idea is this node asks its neighbor, hey, can you give me your information? And it takes its own information and then somehow aggregates them through a permutation invariant function. For example, the sum or the mean or the max, doesn't matter. Some function that does not care what the order of things are. I think Peter want to help. You fine? And then when you have that result, you pass it through. Yes?
Question: is this single layer in the graph in the neural network? Or?
Yes, kind of. So you can, like, one layer updates the node features of every single node. And that's then one layer. So if you have, for example, 3 layers, or let's say 2 layers, like with one layer, information from that node can travel to this node, right? not more. Like this node will never have information from that node. If we have 2 layers, now information can travel from this node to that node to that node. And then we have a 2-hop transversion, exactly with 3 layers and so on, right? If you add more layers, then you can have more information. Yes?
But you cut off this information flow after each time step, right? So, for example, if a node that is 3 nodes removed has a message and it sends it, then it can travel 2 nodes, but in the next time step, that message is not passed on to the node
Yes.
3 removed from it.
Yes.
It gets cancelled.
Yeah. So the idea is that if you have information, like for this node, information can come directly from this node. For that node, it will still be information from here, but it will be through that node and through that node. So it will be altered. If that is, what did you mean? Oh,
Let's suppose the network has 2 layers.
Yes.
There can only be direct connections.
yes.
So you can only ever send messages to a direct layer.
Yeah.
A node that is removed
Mm-hmm.
get a message from the node.
Like this one?
Yes.
Here to here? No. It
So
cannot.
The node state isn't saved for next time step and then picked back up. If you do this iterative the prime series of graphs, for example.
Yes. No, it's not.
Okay.
All right. And then, as I said, like the actual update of the node features is then put through an MLP or any other learnable function. And this is actually then the learnable part. And this network does not care about how many nodes there are because we do it for each node separately. And it does not care what the order is of information because we have this permutation invariant aggregation function. The only thing it cares about is what is the dimension of the node features, because that MLP needs to know how big it is. So this is the idea about GNNs and message passing. Yeah.
So you can also have arbitrarily many neighbors.
Yes.
And I don't know anything about it.
No worries, no worries. And now we get back to this figure, because what we now care about is how can we generate a scene graph embedding? Because for graphs, there are many different tasks, right? Like we could do node classification, we could do link prediction or whatever. And there's also a thing like called graph classification. So we try to classify the whole graph. And we kind of want to do something similar, right? We want to take the whole graph and then pool all over the nodes and get an embedding, which is exactly the same as we do for the image, right? We use a CNN for the image to get an embedding. Now we use a GNN to get a similar embedding. Was that understandable? Perfect. So, yes. The next idea or the next thing is, what graphs should we use for explainable scene representation? Well, it should be a simple graph structure, right? If I have a graph with 1 million nodes, this is not explainable. Like if me as a human looks at that graph, I'm like, okay, that doesn't help me at all. We want objects and relations if possible. So nodes could be, if we go back to the robot-related task, one node could be a robot, another node could be an apple, there could be a knife, and maybe some connections in there because the robot can pick up the knife and then slice the apple. Something like that. Yeah, the edges should connect between 2 objects and possible relations. And the graphs which we want to build should be completely derivable from an image. So if I only give this image, then I should get this graph. So you can think about the graph as a more structured form of the image with additional information because we put in there, okay, which objects could actually interact or relate to other objects. Which also means we could lose information, right? If I don't input everything out of the image, maybe I lose information in that scene representation. So that could look something like this. We have a man feeding horse, horse eats from bucket, man holding bucket. This is the main idea. And those graphs are called scene graphs because they represent a scene. And as I said, if the data structure or the data size is not too big, they are inherently an interpretable data structure. So we already have a data structure which is more interpretable compared to a raw image, where we can say as humans, okay, I see different relations and so on, and then the robots also gets this as an input. The main problem with that is you could now argue, well, if I embed an image, I have a vector. If I embed a graph, I have a vector. So the explainability, again, is like kind of meh, because I, again, need some methods to then reconstruct, okay, what was important in the image, what's important in the graph. But we will get to this later, where we can actually show that we have more advantages with a graph compared to an image. So this is just a short summary of the previous slides, and gives you the opportunity to ask some questions before we get to the next topic.
So like information from the image is passed to the graph like manually, like a human.
We will get to this in the next slides. All right. So let's look at scene graphs. So scene graphs in general, they are mostly used in vision problems, right? They are not necessarily related to robotics or that directly to robotics. And they are used for scene understanding or reasoning and for visual question answering, because it's much easier if you have a question, for example, what's the man doing in the image, to then say, okay, let me find the correct node in my graph. And now I just go through the thing and say, well, the man is feeding a horse and the man is holding a bucket. Done. I've answered a visual question. It's easier than to input the image and then tell the CNN, okay, now need to output me something. I don't know, some sentences, something else. But the question now is, how do we actually get there? Because sure, it's nice image to graph, but what happens in between? It's not that super easy, right? Because we have to somehow get from images to some text-based representation. So a little bit of math, nothing too complicated. If we look at it from a probability distribution standpoint, we can say that the probability distribution given an image or of the scene graph consists, given an image for the scene graph consists of 3 parts. So the first part is we need to get the bounding boxes in the image. So we need to know where are the objects we care about. So we give whatever model the image and it outputs the bounding boxes. The second part is we now have the bounding boxes in the image. Well, now we need to know the object labels. Otherwise, we can't really name them in our scene graph. And the third part is if we now have the object labels, the bounding boxes, and the image, we can finally see what relations are there between different objects. So we have 3 probability distributions, which then define our graph from the image. Like, what is the major problem with this approach? Can you see anything that could be bad? Any issues? Yes.
For example, the probability of bounding boxes already depends on a prior model. So maybe our model doesn't detect all of the information, all of the objects in the image correctly.
Yeah. Yes.
Ideally, we would have one bounding box and not have to consider the distribution over all the bounding boxes for one object.
Yes, for one object, for sure. Yeah. In this case, it's more like, okay, what possible bounding boxes are there for any given object? But yes, it is about the whole thing is prone to errors, right? Like if we look at all 3 together, if we have some error in predicting bounding boxes, this gets propagated to the object labels, and then if there are new errors in the object labels, this also gets propagated to the relations, right? If we have wrong bounding boxes, we get labels for them. If we have right bounding boxes and we get wrong labels, then we maybe also get wrong relations and so on. So it could accumulate. But well, this is the main issue of this method. But usually it's done in this setting. So if we now look at it in practice, well, we have the image, we predict our bounding boxes, we predict our object labels, and this is nowadays, these are even very old methods, not necessarily old, but the idea of them are rather old. We could use YOLO or faster RCNN, right? They work off the shelf. If our data set, if the distributions of our data set we want to use it on match the data set it was trained on. We could also nowadays use a VLM, right? VLM also does this actually pretty good. So this shouldn't be a problem. But then the main problem arises with the scene graph generation model, because now we have all those objects. How do we now create a graph? The naive approach would be, okay, I take every bounding box and I compare with every other bounding box, so a fully connected graph. And then my network says, okay, this connection we don't need, this one, this one, this one, this one, and all others have like specific relations. This needs a lot of time and a lot of compute. So there are also smarter methods where you directly predict the correct relations and do not need to compare every object with each other. But in the end, whatever method you use, you will end up with such a scene graph. Sometimes better, sometimes worse. In general, if you want to read up on some of those stuffs, there are some linked papers. Those are not relevant for the exam, just for you to have a look at what different papers there are and how they execute this stuff. Yes, and then we have a short summary because that was already the introduction for scene graphs. Do you have any questions about how to generate a scene graph or what a scene graph is? Perfect. Then let's get to the next part, which is scene graphs in robot learning, because now we want to see how can we actually incorporate them in robot learning and how can this improve explainability. So there are two methods I put on the slide here. For one, we have on the left this hierarchical planning, where we have a symbolic scene graph and a geometric scene graph, and we can use those two scene graphs to then actually make planning motions, right? Like move to the can, grab the can, and so on. Those scene graphs are rather simple. As you can see on the top, we have can on shelf, can in shelf, can on table. So it's all about like these positional relations and not about the idea of what can I do with the object? Can I pick up the can? Can I put the can on the table? But it still works fine on their defined tasks. And then we have a little of a newer paper, the concept graphs, which we will have a closer look at. So the concept graph thing is we now want to produce a 3D scene graph and use that for later downstream tasks. So we don't train the scene graph generation and the task together. We have first the actual scene graph generation and then use this scene graph for some tasks, some robot tasks. And the concept graphs, the main idea is that we, for the creation, we actually don't need to train anything because we use 2D foundation models to actually create a 3D scene graph. And then we can include object captions, we can include scene structure, 3D object detection, and spatial reasoning, like everything which is on the figure out there. But again, most of the spatial reasoning is the Ottoman is on the carpet or in or whatever. Like that's the main issue I have with those papers. The scene graphs are rather boring. Like they don't tell me much. They just tell me, okay, where are the objects to relation to another object? But that's it. Like in the scene graph itself, there could be much more information. So the concept graph method itself gets an RGBD sequence of images. So the robot is like moving around in the room. Yes?
In the scene graphs, they use essentially voxels or Gaussian stacking?
This is a good question. I think voxels or point clouds. I don't know. You need to look it up in the paper. I'm not entirely sure. But yeah, they get RGBD sequences because the robot is like moving around in the room. And then they have some open vocabulary detection segmentation. So some model off the shelf. I don't really remember which one. Should have written it down. But it's also not important. Like there are a lot out there. then they extract features from the newly detected objects, and then they need to either fuse or initialize the objects, right? Because if, for example, this object is not new, but actually one we already have seen, then we need to merge those features which they newly discovered. But if it's actually a new object, then they need to actually initialize it. And then we can use an LLM to say, okay, we now have a lot of different nodes, a lot of different objects, and we just query the LLM and say, okay, we have object 1 and 2 with specific positions. What is the relationship between them? And I think in the paper, they usually query it with something like, okay, use on or in or whatever, like very simple positional relations. They also tried other relations, but they never used them for then the downstream tasks. So they were only interested in the positional stuff of the different objects. And then we actually have this 3D scene graph, which then again is used for downstream tasks, but they actually put the 3D scene graph again in an LLM for the planning. So we first used the LLM to create it, and then we put it again in LLM, which is kind of useless in my opinion, but yeah, it is what it is. I guess also in their paper, such a scene graph is more about actual textual prescription of the scene, and it is not seen as like, okay, in my node features themselves, there are important informations. So that's the reason why they use an LLM. But they actually then can use it for plan-based robot learning, where they have navigation, robot manipulation, or any other downstream tasks where the robot has to find different objects in a room, where it makes a lot of sense, right? Like if you have scanned all the rooms and then you have this big scene graph and you put it into an LLM, the LLM can then say, okay, my robot is in this room, he needs to go to this, because there are different relations between the objects, and I can just go through the graph. So for navigation, this makes a lot of sense. Okay, any questions? Yes.
Yeah, quick question. Because basically, so we have the, let's say, text information that object 1 is still with position, point, and then we use an LLM to get some more information. Then we encode that into a scene graph, and then we pass it to another LLM, right?
Yes.
Why do we not keep the whole text representation, passive text representation as it is to?
I don't know. Maybe it could be that they keep it as a text representation, right? I do not think that they first go into this graph and then again you get text, but they rather use directly this text, and this one is rather to use it for humans to show like, hey, this is our scene graph, that's how it looks. And they also, in their paper, they also evaluate the scene graph generation itself. So it makes sense for them to first generate a scene graph and then evaluate, okay, how good was the scene graph generation? Because if that's already bad, then that could indicate that also the whatever the LLM then predicts for the planning is also bad. Any more questions? All right. So let's get to the last part, because it's nice and all that we have scene graphs, which are inherently a little bit more interpretable, but how can we further improve explainability? And this now goes more or directly in the direction where I'm looking into in my PhD. So the main idea we look at is goal-driven explainability. And the idea here is that I can use such a graph to make any predictions I want. Let's say we are in the visual question answering, and I tell my model, hey, what is the man doing in the image? And the model says, well, he's playing baseball. And now the model can explain its decision by telling me which nodes were important, or which relations between which nodes are important. And in this case, it could be the helmet and the racket, and of course the man. And that's how it makes its decision, right? For us human, it makes sense, because only because a man is wearing pants and shirt doesn't mean he's playing baseball. So this is the main idea of using such graphs in a goal-driven explainability case. And if we now look at robot learning with this approach, we first get an image, we get a scene graph, doesn't matter how, just black magic. We have our fully connected scene graph in this case. And we put this through a GNN, which gives us a graph embedding, and then we put this into our action prediction model. So this graph embedding is actually then the whole scene representation, which we could also get from the image as using a CNN. And then we get an action and put this in our environment. And the question now is, where does the goal-driven explainability happen, right? Like, where do we get this subgraph or this importance graph, which explains to us, okay, why did the robot choose the action it chose? And well, for one, we need an explainer to get this explainability. And then there are two options. We could do it post-hoc. So we train our GNN, our whole model end-to-end on our fully connected graph. And then in the end, say, okay, if you now do this rollout, please explain to me what nodes were important. Or we do it intrinsically. So this means if we have this fully connected scene graph, now we first want to sparsify, right? Because a fully connected graph does not tell me much, but I could actually use some other GNN layers to then say, okay, cut some of the edges and tell me which nodes for this task are important and which are not, or which do you feel are important. And this is also important to note that in the intrinsic case, the action prediction model is trained on this subgraph of explainability. So it could be that there is a lot of information which the model actually does not get, but should then still perform equal to when it gets the fully connected graph. If we do it post-hoc, the model actually gets all the information there is in the fully connected graph, and then post-hoc we see, okay, what are the explanations we're looking at? Which is again one of the main issues with explainability, because if we increase explainability, usually we decrease performance with that. And the other way around, if we increase performance, we decrease explainability. And our main goal is that we have just both on high standards. And in practice, this is one scene graph for a closed drawer task, post-hoc. I would say this is not interpretable. Like, there are a lot of nodes, and as you can see, there are some edges which have a 0 weight, but there are a lot more edges with a weight of 1. So if I train my model on a fully connected graph, and then try to do post-hoc explanations, it looks kind of messy, not really nice. On the other hand, if I do it intrinsically, I have the main advantage that I can tell my model which nodes I think are important and which it should focus on. Of course, you could also just let it train without telling it what nodes you think are important and just see if it finds some nodes the model thinks is important. But currently we have the issue that then it just focuses on the robot and that's it, on almost nothing else. So in this case, we told it, hey, if you want to close the drawer, maybe you should focus on the robot and on the drawer and the counter, because the drawer is in the counter, right? And then if we did it on a rollout, it was actually successful in doing the task, but still like excluding all the other nodes, which are not necessarily needed for the task execution. We also did it for turn sync spot. So it just had to go forward and turn it. And we also told the model during training, hey, the sync should be included because it's important for turning the sync spot, right? Which in the rollout, it did not include. So even in the intrinsic case, and even if we tell it, hey, those things are important and those are not, there are still some mistakes. But this is in a direction where we can now say, okay, the graph is not only something fully connected, which is inherently interpretable, but we can actually also condition the model on a subgraph, which for us humans is more understandable, right? Like if my model still executes the task on the same level with a fully connected graph and then with a subgraph where I can say, okay, those 5 nodes are important, then this makes it for me more interpretable, because then the model works with the same information I would work by completing this task. So advantages of graph explanations compared to like the image explanations. So in general, scene graphs themselves offer already interpretability compared to raw image, just because we have, if we think about the normal scene graphs, we have relations between objects, and we already have an abstraction of what objects are in the image and what objects could be relevant. Then if we look at the heat map for example, the GradCam, In the image-based case, it's more of where is the explainability. And if we look at the graph explanations, it's more on what and how, just because of the given structure of a graph, right? We see which nodes are important and which are not. Heat maps are easy to grasp, but are rather shallow. And graph explanations, they are a little bit harder to understand, but give you a deeper explanation, just because, as I already said, of their structure. And heat maps are post hoc, and graph explanations can be applied also intrinsically.
Can we have the same problem as with heat maps here, that we can have a heat map that focuses on things that aren't really important? And now we could have a graph that focuses on things that aren't really relevant and that one doesn't really use?
Yes, yes, that could happen. Like there are cases, like you could imagine, let's say I want to grab this bottle, and in every scene I have this owl, and I always grab it from the right. And then this owl moves to the left, and the bottle also moves to the left, and now I have to grab it from the left. And then it could be that the model does not focus on the bottle, but focuses on the owl to then distinguish, okay, when should I grab it from the right and when should I grab it from the left? Because the owl is more consistent in moving the route. So yes, there are definitely cases where the model could focus on irrelevant objects.
Would you always see that in the scene graph?
In the graph. I didn't understand.
Would you always see that in the scene graph?
Yes. Like if but one in this graph, it focuses on everything, right? And also in this graph, if we do, like, this is a rollout, right? This is not during training, so it has learned to focus on those 5 objects. But if suddenly this object also is relevant, then it would be in the graph. Then we could say, okay, why the fuck did it focus on this object? Like, is there some bias in the data and so on? But yeah, I think also in the graph, it's more easily observable if there are any objects which should not be relevant to a task compared to a heat map, right? Because heat maps is more like, okay, focus. Yeah, exactly. But yeah, it could also happen in the graph. Yes.
Is the next relation between the C graph and the graph neural network, or is it just the same thing? I mean, there is like an arrow between the image, the C graph, and then the GNN. But what is, yeah.
Like we use the GNN to create an embedding of the C graph.
Okay. So what shape does the GNN have in general? Is it the same shape, for example, as the C graph, or is it just a more general thing that you use as a neural network?
The GNN, as I said earlier, the GNN itself is not a graph. So it's not graph based or whatever. The GNN is just a concept to work with graphs with neural networks. So the GNN itself has, let's say, 4 layers, and each layer does the things I explained earlier and has one MLP, which then produces the new node embeddings. That's it. And the MLP shape, this depends on the node size of the node features. Yes. So, yeah. Any more questions? Otherwise, I'm at the end of that lecture block.
Maybe I do have a question regarding the graph neural networks. As we've seen, there was a transaction between one node and the other. Multiple transactions per layer allowed, or just one?
Just one. Right. Yeah.
Like for an explainer, we're basically using the same graph, but we somehow made some nodes more like to pay attention for.
Yes. So the explainer for the post-hoc example, or maybe it's here. I think it's here. Okay. So for the post-hoc example, the explainer looks at, it tries out different subgraphs of our graph. In this case, I think it's only edge-based, so we can't really remove nodes, but we can remove edges. And it tries out to remove as many edges as possible, but still producing the same embedding as before. Right? If I, for example, could remove all this and still get the same embedding from my GNN, that would mean that all of this is not necessary. And the explainer looks at the graph and tries to find out, okay, how many of the edges can I remove to only minimally change the embedding I produced. And in the intrinsic case, it's a little different, because in the intrinsic case, we tell the model, try to remove as many edges and then also nodes as possible, but still performing high on the action, right? Because it's end-to-end. We can say here, the explainer, okay, fully connected, make it a subgraph, and then the action should still be good, right? And then it propagates through the whole network. And then it can say, okay, I can't remove all 18 nodes, I need to keep 5 or whatever. And in our special case I just showed, we can also tell the network, hey, those 5 are important, the rest you can disregard. And then you have like 2 different losses, right? For one, the action prediction loss, and the other one is this focus on those 5 nodes loss. Yes.
In this method, do we still have relation types in the graph?
Not yet.
No.
Like in the beginning, I tried with relations, like in the direction of affordances, what I could do with objects. Currently, we only look at what objects could be related to others. So there are no relations implemented yet, but it would be still a fully connected, or not necessarily fully connected graph, but it would be a graph where I then put in, okay, I can pick up this object, I can put something on this object, and then I would try to work with this. But currently, we are more in the direction of trying to prove that my robot model still learns the same when using a scene graph compared to an image. All right. So yes, if you are now very much interested in scene graphs and robotics, feel free to write an email. Like, I'm always open for, I think all of you are in the master, right? So always open for master thesis, or if you want, you can join our seminar in Practica, which next semester will be about XAI. That could also be interesting. Yes, and then I would say we do the 5-on-5, and then we continue with the next lecture. All right, thanks.
Ja.